so now what we want to look at is we're going to look at gas vapor mixtures. So we've looked at ideal gas mixtures, and now we're going to introduce typically water vapor, but what we're doing applies to other things. So if you're looking at gasoline and air going into an internal combustion engine or something like that, what we're developing is applicable, but what we look at in terms of practicality, in terms of this course, and what we'll be looking at next in terms of air conditioning is water vapor and air is important. And so what we're going to look at now are gas vapor mixtures. And so what we're going to look at is typically here we'll have water vapor and air. And we're going to assume that the water vapor and the air are ideal gases. So I can use the values that I find for water vapor in table A1 when I'm treating it as an ideal gas. And we're looking at that as a highly superheated vapor. So the water vapor in the air that we're breathing is a highly superheated vapor. Which is why we can consider it an ideal gas. So if I'm going to take a piston cylinder, and what I'm going to do is I'm going to have my air vapor mixture in here, and I know that the total pressure P is equal to the pressure of the air plus the pressure of the water vapor. So I'm going to be looking at that and looking at what it is, and let's look at a TS diagram to see where we are with everything. And using the TS diagram is very useful in terms of conceptualizing how I'm going to think about different things that we're going to define in terms of how we tell the state of this air vapor mixture. So if I look at a TS diagram, and I'm looking at the water vapor now. And here's the partial pressure of the water vapor, and I'm at some state 1. So I'm at some, it's highly superheated vapor. So this is what I have here. And now what we're going to do is we're going to introduce certain terms that are associated with this. And so what we're going to do is cool the vapor down. So we're cooling the mixture down. As we cool the mixture down, the water vapor goes down. Cool mix to T2. And so what we're going to do is, if I look at that, if I cool it down, the vapor stays a vapor. The water vapor doesn't change until it reaches this saturated point here. So at this point, if I cooled it any further, I'd get condensation. But until I cool it down there, the partial pressure of the water vapor remains constant. It's a constant pressure process for cooling until I get to this point. And this is called the dew point. So if I cooled it further, to T3, then I would be down here at 3, and the water vapor would be here, but I'd also have some liquid around as well. So I have some liquid around. And so we are going to talk about this, and we're also going to talk about something here, which I'm going to call 5. And so state 5 is the partial pressure if the air, so this would be a piece of G. And what I want to be able to do is that P sub G is equal to P sat at T1. So if I take this and I look at what is the saturated pressure associated with this temperature, it would be here at state 5, this PG. So these terms will matter. So now let's say that we have the following mixture, and I'm going to use English units here because this will align with what we do in air conditioning work, where our common practice uses English units. So let's say that we have PV is equal to 0.256 psia, P total is 14.7 psia, T1 is equal to 80 degrees Fahrenheit, and P5 would be equal to 0.508. So if I went in the steam tables at 80 degrees Fahrenheit, I looked up the saturated pressure, P sub G would be 0.508. And I don't remember the number of the table, but anyway, if I did that, I would find that. If I cooled this, and for this, T sat is equal to 60 degrees Fahrenheit. So T sat at this partial pressure. So now if I cool this down to 60 degrees, that's the dew point. So if I cooled it below 60, condensation would occur. So let's say, so if you cool to 60 degrees Fahrenheit, that's state 2. And if I cool it any further, then condensation occurs. Let's say I do cool it further, and I cool it to 50 degrees. Then if I cool it to 50 degrees, so in this case T3 would be 50, P sub 3 is equal to P sub G at 50, or P sat at 50, and so that's equal to 0.178. So as I cool it down, the partial pressure, and it condenses, the partial pressure of the mixture associated with the water vapor decreases. And now we need some definitions, because we talked about relative humidities. You say, what is it like out? The relative humidity is, I don't know, 70%. Oh yeah, it feels hot. And so what does this mean? What's the definition? And so what we want to do is make sure that we understand what these definitions are. And so let's look at that. So the relative humidity, and so this is equal to the mass of vapor at state 1 compared to the mass of vapor at state 5. So phi is equal to m1 over m5. And I can use the ideal gas law, so this is mv over the mass of mg. So this is equal to pv v over rt over pg v over rt for water. So this is equal to pv over pg. So the relative humidity is this mass ratio, but I can tell it in terms of this. So if I can determine this, it enables me, and we'll see that the relative humidity is relative to what the PG value is. So the higher the temperature, the higher the PG becomes. And so now what we want to look at is, we'll do some examples and put in some numbers associated with this. So let's say the weather is 80 degrees Fahrenheit. The relative humidity is 70%, and we want to find P sub V. So P5 is equal to P sub G is equal to 0.508, and this is P sat at 80 degrees Fahrenheit. And PV is equal to 0.7 times P sub G, 0.508, is equal to 0.356 psia. And so then P is equal to 14.7 is equal to PA plus P sub V. So PA is equal to 14.34 psia. So when I'm using the ideal gas mixtures, I want to be able to pay attention to this. I want to be able to pay attention to this. Now, one of the challenges that we have with relative humidity is that it's relative, and so in engineering work that isn't as handy as having something that is the actual mass. So we have something called the humidity ratio or specific humidity. So it has two terms associated with it, and so this provides us with direct information that we can use. So we have something called the humidity ratio, or specific humidity, and so omega is equal to the mass of vapor over the mass of air. And I can use the ideal gas law, and so I can use that MA is equal to PA V over RAT. So I can put that stuff in, and I can do it for MV is equal to PV V over RVT. And if I substitute this in, I get that omega is equal to 0.622 P sub B over P sub A. And I can have that the relative humidity is equal to omega PA over 0.622 PG. So these are useful equations that we'll be using in problem solving. And now, to use it in problem solving, we'll do heat transfer from a tank, we'll have condensation occur, everything happens, and we'll find out how to use this relative humidity. We start off with that term, and then we end up having to calculate what's going on. So we're going to have a tank, 50 cubic meter tank. Cubic meters, cubic feet rather. We're going to have P is equal to 14.7 psia, 110 degrees Fahrenheit. P is equal to 70%. And we're going to cool it to 50 degrees Fahrenheit. We want to find the heat, and we want to look at this process. So we're going to do a first law analysis on this. And so we have, it's a closed system. The substance is gas vapor. The process is V equals C. And we certainly have energy involved. And so let's look and see what we have in terms of the processes involved. And then we'll get involved with finding the change of internal energy, the heat, and everything else. So when I look at this problem on a TS diagram, I'm basically starting here at state 1, and I'm going to go down here somewhere at state 2. So what's going to happen is I'll have condensation. I'll have condensation occurring here. And so this is our line PV2, PV1. So I know if I start off at 110 degrees and 70%, it's going to have condensation occur. And this becomes part of the process that we look at. So now what we want to do is to be able to find out what are the properties at state 1 and state 2. And to do that, we need to find the pressure. So at 110 degrees Fahrenheit, Psat is equal to 1.278 psia. So P sub V1 is equal to 0.7 times 1.278 is equal to 0.895 psia, and P air is equal to 14.7 minus PV1, and so that's equal to 13.805. We'll see how much liquid came out. So we'll look at the liquid that comes out in just a second.